In this video, we will learn about Sieve of Eratosthenes. We will look at its concept, we will go through the code, and we will try to solve a general problem. So let's get started. So what is Sieve of Eratosthenes? Well, it's an algorithm for finding all the prime numbers in a given segment from 1 to n. The most important aspect of this particular algorithm is that it runs in n into log of log n time complexity. Okay, let's directly deep dive into the algorithm. So the algorithm is that we write down all the numbers. We have 1, 2, 3, 10 till n. Then we start from 2 and we will mark all the multiples of 2 as false. This will be false, this will be false, 8 is also going to be false, and 10 is also going to be false. Then we will go to the next number, which is 3. We will check whether 3 has been marked false or not. If not, then we will take 3 and do the same. Now we will mark all the multiples of 3 as false. We will mark 6 as false, which has been already marked as false by 2. Then we will mark 9 as false, similarly till n, right? Then we go to the next number, which is 4. Now 4 has been already marked as false, so we will not do anything. Then we go to 5. Then for 5, we will process and do the exact same thing. We will go to the multiple of 5, which is 10, and we will mark it as false. And then we will go to 15, we will mark it as false, and we do the same. If we encounter a number which is not marked by any of the previous numbers, then that means that number is a prime number. So that's how this algorithm works. It iterates on every single number, and if that number has not been marked false, then we take that number and mark all its multiple as false. Simple as that. This is very straightforward algorithm. We don't even need to go into the depth of it. Just for the teaching purpose or the sake of teaching, I will highlight the observation that we are using here. A number is a prime number if none of the small numbers are actually dividing it. Very clean and straightforward observation, right? So let's say you have a number x. All the number greater than x will not divide x, so we don't even bother about them. All the numbers which are smaller than x, we are only going to consider those. Now there are two possible cases. A number can be a composite or a prime, right? Let's say you have a composite number called as y. Now that y divides x. Now y is a composite number, so it will have prime factors as well, py. So if y divides x, then py will automatically divide x, right? So that's what this observation tells us. A number is a prime number if none of the small prime numbers divides it. We don't even have to bother about the composite numbers, because if a composite number is dividing something, then all its prime divisors will also divide that number, right? See, y is a composite number. It is dividing x, and py divides y, and py is a prime factor of y. So ultimately py will also divide x. Hopefully this is clear to you. A very simple and straightforward observation which is directly derived from the definition of a prime number. Let's take this an example for better understanding. Let's say you have this array and you start from 2, right? So you iterate on this entire array, and if that number is not marked as false, we will take that number and mark all its multiple as false. So let's start from 2. See, 2 is not marked as false, so that means that number is a prime number. So I am going to circle it with blue color, and now we will mark all its multiple as false. So 4 will be marked as false, 6 we will mark it as false, 8 will mark it as false, and 10 will also mark it as false. Now we'll go to the next number, which is 3. Now 3 is not marked as false yet. That means this number is also a prime number. Now we will mark all the multiples of 3 as false. So we'll mark 6 as false, and we'll mark 9 as false as well, right? Then we go to 4. Now 4 has been marked as false. That means this is a composite number, so we are going to ignore it. Then we go to 5. Now 5 has not been marked as false, so that means this number is a prime number. Now we'll mark all its multiple as false. So 10 will be marked as false. Then we go to 6. 6 is already marked as false, so we ignore it. We go to 7. Now we mark all the numbers which are divisible by 7 as false. So there are no numbers in this particular array which are divisible by 7. Okay, so now you have all the numbers which are prime numbers. from 1 to 10. So this particular algorithm is used to find all the prime numbers from 1 to n. Here n is 10. So now we have all the prime numbers from 1 to 10. 2, 3, 5 and 7. Now if you observe carefully, when we were processing number 3, we marked 6 as false. But 6 has been marked false by 2 already. So we are iterating from left to right. So we don't need to consider all the multiples of 3, like 3 into 2. We don't need to consider, because 2 will already process that and mark it as false, right? So we can start directly from 3 into 3. We don't need to start from 3 into 2. Same thing goes for 5 as well. We don't need to start from 5 into 2, then we go to 5 into 3, then we go to 5 into 4. We don't have to do all these things. Why? Because 5 into 2 will be processed at the time when we were processing 2. It will mark it as false, right? 2 into 5. Same thing, 5 into 3 will be processed at the time when we were processing number 3. It will mark it as false. 3 into 5 will be processed by 3. Simple as that. 5 into 4 will be processed at the time of 2 itself. Why? Because 5 into 4 is ultimately 5 into 2 into 2, which is 10 into 2. Right? When we were processing 2, we marked all its multiple as false. So we would have already marked 10 into 2 as false as well. So we can start from I into I. This is the main observation that we get from this. So by using our latest observation, let's try to follow the algorithm. Let's start from 2. We haven't marked 2 as false yet. That means 2 is a prime number. So let me highlight 2 is a prime number. Now we start from I into I, which means we start from 4 and we start marking. So 4 will be marked as false, 6 will be marked as false, 8 will be marked as false and 10 will be marked as false. Then we go to 3. 3 hasn't been marked as false yet, so this is going to be a prime number again. Then we are not going to start from 3 into 2. Remember, we are start from I into I. So we directly go to 9 and mark it as false. So we directly go to 9 and mark it as false. See, earlier we went to 6. See this? We went to 6 and we marked it as false. But now we will directly go to 9 and mark it as false. Why? Because 6 has been marked as false by 2 already. So we go to 5 and 5 is a prime number. So when we are processing 5, remember we start from I into I, which is 5 into 5, 25. We will not process 10. Earlier we processed 10 here, right? See, here we process the 10. But now we are not going to process it. Why? Because 2 has already marked the 10 as false. So we don't need to process it again. So we can directly go to 5 into 5, which is 25. 25 is out of range, so no need to worry there. After that we have 7. Again, 7 hasn't been marked as false yet, so this is going to be a prime number. See, these are very simple and straightforward. I hope this is clear to you. Let's go through the code. Is prime is the array that we have. Initially, everything is marked as true. We will start iterating from 2 and we will go from left to right, that is smaller to larger numbers. And then inside we have another loop. We will execute this particular loop to mark the numbers false. But we do only if the current I is prime number. Remember, we are processing that number if and only if that number is a prime number. We never processed 4 because 4 has been marked as false by 2. So we don't process a composite numbers. Why we don't process composite number? Well, we discussed that while we were discussing this observation, right? A number is a prime number if none of the small prime numbers divides it. We don't need to worry about the composite ones. So that's the logic we are following here. So we have is prime array. Initially everything is true. We start from 2. We check whether that particular I is prime number or not. If that number is a prime number, then we go to I into I. Why we are not starting from I into 2 or I into 3? We have already discussed that here. So we start from I into I and then we iterate till n. We increment it by I so that we visit all the multiples of I and we mark them as false. Straightforward and very clear code. Now this particular algorithm has a very unique time complexity, which is O of n into log of log n, right? But before we dive deep into this particular time complexity, let's first understand the time complexity when we are not checking for is prime. we start from this outer loop and we directly go to the inner loop and mark the multiples as false. The key observation is that when we ignore is prime check from that if condition, the inner loop runs n by I times for every single I. So total number of operations will be n by 2 for 2 plus n by 3 for 3 plus n by 4 for 4, like that, right? We can take n as common and we have something like this. Now we know 1 by 2, 1 by 3, all this is bounded by a log n. So the entire thing will be bounded by n log n. So when we remove this particular check, is prime check, we are not considering this is prime check, we are removing this if condition altogether. Then we get the time complexity of n into log n. Now let's consider this is prime check. So we said that the inner loop runs n by I times for I is equal to 2, 3, 4, 5. But when I is equal to 4, the inner loop will not execute. Why? Because of this is prime check. 4 is not a prime number, so this will be marked as false already by 2. So the inner loop will not be running for composite numbers like 4, 6, 8. The inner loop will not run for these numbers. So the inner loop will run only for the prime numbers. So you will have something like n into 1 by 2 plus 1 by 3 plus 1 by 5 plus 1 by 7, something like that. That's why this log of n gets reduced to log of log n. Now how exactly we arrive to log of log n? Well, there is an involvement of some kind of integration and calculus portion here. So I'm not going to deep dive. We can deep dive, but the length of video will increase. Hence, the most important fact is that we are not processing the inner loop for every single I. We are processing only for the prime numbers, right? And that actually reduces our time complexity from log n to log of log n. That's the main concept that we need to understand here. So let's take a problem, a simple problem. So the problem says that we need to find all the numbers till n who has exactly two distinct prime divisors. So we are now going to maintain the prime divisor count. Now if you look at the inner condition, we don't have the is prime array now. Remember why we used is prime array? To check whether a given number is prime or not, so that we can execute the inner loop. But we can do that using prime divisor count array as well. If prime divisor count of I is 0, that means that particular number I is a prime number. Then we will execute the inner loop. Now there is one more highlight here. We are not starting j from I into I. See, let's go back. See here, j started from I into I. And we gave a very good proof as well by taking this particular example. Right? Why do we need to start from I into I? But now we are starting j from I into 2. Why is that? Well, earlier it was very straightforward, the reason why we needed I into I. Earlier we were only marking number I as false or true, right? So if number 10 is marked as false by 2 while we will processing 2, there is no need to again mark it as false while processing 5, right? That's why we started the j value from I into I. But now things are different. We are not just marking true and false. We actually need to maintain the counter. We need to increment. Whenever we encounter a number that divides that particular j, we need to increment the counter for that. That's why we are starting from I into 2. I hope that makes sense. Now, once you have the entire counter, we can check how many divisors and I have, how many prime distinct divisors and I have. If they are 2, then we can increment the answer. So I selected this particular problem to tell you a very important thing, that the starting point of j you need to decide based on the requirement. It's not going to be always I into 2 and it's not always going to be I into I. Based on the requirement, what you are going to do inside this particular for loop, you will decide the starting point. So if you remove this if condition, our algorithm will have O of n into log n time complexity. To achieve n into log of log n time complexity, you need this particular check, so that the inner loop will be executed only for the prime numbers, not for the other numbers, not for the composite numbers. So you need to decide what if condition you are going to put here. So at the end, you will decide two things. the if condition and the starting point of j. I hope this is clear. I purposefully selected this particular problem so that I can highlight this. In this video we learned Sieve of Eratosthenes. We went to the core concept. We discussed the entire approach. We took an example and we proved our observation. By using this example, we proved our observation. A number is a prime number if none of the small prime numbers divides it. By using that observation, we coded this particular solution. We also highlighted why we are starting from I into I. And we managed to prove the time complexity as well. Actually, we proved n log n, but we can prove n into log of log n as well. For that, we have already highlighted the very important step that the inner loop will run n by I times and only for the prime numbers, not for the composite numbers. We have already highlighted that as well. Then we went to a problem. This problem was selected purposefully so that I can highlight the starting point of j and a condition. Hopefully everything is clear. If something is missing, please do comment. I will make another video highlighting that.